Please take your seats. Our program is about to begin.
Good morning, everyone, and welcome once again to FCRC, the Federated Research Computing Conference, the 9th in the series since 1993. This is the 4th plenary session, which we're very happy to have. We'll have Delma, our plenary speakers chair, to introduce this speaker today. I just wanted to, I'm Timothy Pinkston, the FCRC chair from the University of Southern California. My preferred pronouns are he, him, and his. I wanted to remind everyone that if you have a t-shirt ticket, please be sure to pick up your t-shirt at the registration desk as soon as you can, sometime today. And we're happy to make sure that everyone gets a t-shirt, which, in case you haven't noticed yet, it says that we will be reconvening in the month of July, a month from now. So, but all jokes aside, we welcome everyone, all of the associated conferences, 14 conferences are here, and we welcome all of you to FCRC. With that said, I please join me in welcoming Dilma to the podium.
Hi, everyone. So I'm Dilma da Silva, and I work with the ACM and team to put together the plenary speakers and the plenary panel. I'm from Texas A&M University, and I'm currently at the National Science Foundation. My pronouns are she, her, hers, and I'll be telling you about our speaker. Before that, let me tell you how it will work. So we have the talk, and there is time reserved for your questions. We have microphones on the aisles on the side, so you can queue it up when you see that you're getting close to the end, okay? So it is my honor to introduce Towsley. He's a distinguished professor at the University of Massachusetts in the College of Information and Computer Sciences. He has made seminal contributions to the design, analysis, optimization, and control of networks. More recently, he and his colleagues have pioneered the information theory of covert communications and the design, analysis, optimization, and control of quantum networks. Professor Towsley was co-founder and co-editor-in-chief of the ACM Transaction Zone Modeling and Performance Evaluation of Computer Systems, and he has also served as editor-in-chief of the IEEE ACM Transaction Zone Networking. He's a corresponding member of the Brazilian Academy of Sciences and has received several achievements awards. I'll just, list a few. 2007 IEEE Koji Kobayashi Award, 2007 ACM Sigmetrics, and 2000 ACM CCOM Achievement Awards. Also the 2011 InfoCom Achievement Award. And very many Test of Time and Best Paper Awards. And he's also a fellow of ACM and IEEE. So join me in welcoming Professor Don Towsley to our plenary session.
Thank you. So thank you for that introduction. It's really great to be here and to be able to talk about a topic that really is very dear to me. I should tell you that I got into this area of quantum networking about 5 years ago. And I did it because 15 years ago, I met up with a colleague in a classical networking project who had trained as a quantum information theorist, quantum communications person, but the company that he joined didn't have quite enough funding for him. And so I got to work with him. His name is Saikat Gua. And throughout the 10 years, he kept telling me that I should start looking at some of the issues in quantum networking, that he thought I would find them really, really interesting. And so for the longest time, we would have these like 2-hour meetings every 2 or 3 months. He'd have to teach me quantum, and then we would start discussing research. And then 5 years ago, it sort of clicked, and I came to realize that he was absolutely right. And so what I'd like to do is to talk about some of the work that I've been involved in, having to do with quantum networks, and sort of raise what some of the challenges are and why you might want to get involved in this, okay? So we're interested in sort of a quantum internet, and the vision is that we're going to have a quantum network that's going to enable full quantum connectivity between pairs of users, multiple user groups, to be able to do all kinds of really fascinating and important applications, as I'll sort of mention on the next couple of slides. And this network is going to have like quantum switches, quantum routers. We're going to learn about quantum repeaters throughout this talk. And as I said, it'll serve a variety of applications. So what's the key ingredient for this? It turns out that it's quantum entanglement, also known as Bell states. You'll sometimes hear them referred to as Bell pairs. And it's entanglement between pairs of remote, let's say, quantum processors. So we have Alice and Bob, and they share entanglement. Think of it that each of them has an entangled coin that either can be up or down, and it's in a superposition, a strange state where it's sort of both at the same time, okay? And the entanglement means that when Alice goes to check, to measure her coin, it will snap to one of the states, let's say up, and what will then happen is that if Bob then goes to measure, he will always achieve the same state. So they were entangled in a way such that when one of them instantiated, that it determined what the other one. And it doesn't matter whether Alice and Bob are in the same room or on different planets. And this, of course, was sort of the theme of the Physics Nobel Prize last year, if you remember, where that was given to 3 experimentalists that essentially sort of showed experimentally that entanglement exists and that it can't be explained by classical theory. And Einstein referred to this as spooky action at a distance. So why would we want a quantum internet? Well, it turns out it would support a number of applications that would really be useful. We would be able to get security as best possible according to the laws of physics, and there's been a lot of work on quantum key distribution, and the network would allow us to do this, let's say, at great distances. We could also support distributed quantum computing. In the news, you read about these quantum computers that Google and IBM and Microsoft have that have, let's say, 50 qubits, 100 qubits. They're very small, and so it would seem like if we could connect them with a network, we might be able to use them to solve large problems. It's also shown to be useful for high-resolution sensing and could be used to allow telescopes, let's say, that are sort of separated by hundreds of miles, to be able to get much sharper pictures of different parts of the universe. And an application I'll say a little more about would be for teleporting, transferring quantum data, let's say from Alice in one part of the country to Bob in the other. So I want to delve in a little bit more about entanglement. And let's start with what classical and quantum bits are. The classical bit has only 2 values, 0 and 1. And it's easily represented by a 2-state device. You can think of it that you could have a circuit that either it has a low voltage which could be interpreted as 0, or a high voltage that would be interpreted as 1. On the other hand, a qubit is represented by a two-state quantum mechanical system, and one canonical example would be light polarization. You could have it polarized, let's say, as sort of a horizontal plane, interpret that to be a 0, or it could be on a vertical plane, and you could interpret that as being a 1. And in quantum notation, they use this bracket notation, and so you see it written as I have on the slide there. But there's one important difference. With the light, it can be polarized at any angle. Actually, it has even more degrees of freedom, but at any angle. And so you have this notion that a qubit can be a superposition of, let's say, the two states 0 and 1. And it would be a linear combination. The coefficients are complex. When you square them and sum them up, they add up to 1. And so you have an infinite number of possible states that a qubit could have stored. Now, getting to entanglement, we can now think of it that we have two qubits, and these qubits can be in combinations of the state 0, 0, 0, 1, 1, 0, 1, 1, and they could be in superposition in sort of the same way as a single qubit. And when you have two qubits, we say they're entangled when you can't describe the state of one of them independent of what the state of the other one is. And a canonical example of that is what's called a Bell state. And you can think of it that the qubits are in the superposition that they're both 0 or they're both 1, and with equal amplitudes. And this has the following implication. Suppose Alice, let's say that we give the first qubit to Alice, the second one to Bob, and Alice goes ahead and measures her qubit. And she's going to get either a 0 or a 1. If she gets a 0, then what will happen when Bob measures his qubit is he will always get a 0. And if Alice had measured a 1, then Bob will always measure a 1. And again, it doesn't matter whether Alice and Bob are in the same room or whether they're light years apart. And so what you can do, one application is you can generate shared randomness across distances. And that's really one of the ways that you can generate secure keys. And it just has applications all over the place: quantum computing, quantum key distribution, as we're going to see, quantum networking and quantum communications. So with that in mind, I'd like to return to this application that our network, our quantum internet would support, namely teleportation. And the idea here is that we would have Alice and Bob sharing a Bell state, sharing entanglement, Alice having some qubit with a quantum state that she would like to transfer over to Bob. And teleportation is all about doing that using the Bell state as a resource. And so what Alice would do is entangle her two qubits, do some kind of a measurement. I'm not going to go into details. When she does the measurements, those qubits are going to produce two classical bits, let's say 1 and 0. The entanglement will be gone. And the question is, what does Bob have on his side? And so Alice then just sends her two bits classically, and Bob uses them to pick an operation to apply to his qubit. And what comes out then is that he has the state, the quantum state that Alice wanted to transfer. And this is sort of the foundation for, let's say, doing distributed quantum computing. So why don't we have a quantum internet yet? And all I can say is it's hard. And the reason is that if we're going to be able to design and deploy it, we have to deal with loss and noise. And so I want to talk about those. So let's say Alice wants to send, let's say, a qubit to Bob, okay? Let's say over a distance L. Well, she'll prepare her qubit, let's say put it in a photon that qubit, and the problem is it's likely to get lost. She could try again, it gets lost. Eventually, she makes it to Bob. Turns out that the capacity of this channel decays exponentially with the distance or the length of the channel. And that's not what you see in classical communications. And so it poses a real challenge. So you could say, well, what if we amplify the signal? That's what we would do classically. And the problems, there's a no cloning theorem that says that quantum signals can't be copied, which means that you can't amplify them. Talk a little bit about noise, okay? If you take two classical bits, let's say low voltage, high voltage, they are robust to slight changes in the voltage. The voltages could change some, but it's very easy to restore them back without affecting the bits themselves. In the quantum world, we saw that a quantum state or a qubit can take an infinite number of states. And so suppose that you started off that the qubit was in state 1, and what could happen is the noise might shift it into a superposition between 0 and 1, and there's no way of telling that that isn't a legitimate quantum state or that it's an error because of noise. And one big source of this problem occurs with quantum memories, where when you store a qubit, they have limited coherence times. And here I'm showing that, let's say your memory can either store a state 0 or state 1. Let's say you store a 1, and what happens over time is it sort of decays and goes into superposition with 0, and then eventually, perhaps because the 0 is a low energy orbit of an electron, it goes to a 0. And so there is sort of a limited amount of time that you can be sort of comfortable with the qubit in memory. So what I'd like to do is to start by talking about handling loss in a quantum network, and then I want to talk a little bit about noise. So what has been proposed is the introduction of what's called a quantum repeater. Okay, we have Alice and Bob. The repeater is going to be a device in the middle with lots of quantum memories that will be used to store entanglement. And the way that it'll work is we'll sort of go through repeatedly 2 phases. In the first phase, the links will attempt to generate link-level entanglement, in other words, Bell states between Alice, Bob, and the repeater. And this is going to be probabilistic because of the what we saw before, the sensitivity to loss. Once those Bell states are prepared, the repeater will perform a Bell state measurement, also known as a swap. And what that does is it propagates the entanglement to the end nodes. And if you delve into this, what you'll find is that it's an application of the teleportation protocol that I showed you before. Okay, and so and something that I didn't point out is now, because of the fact that you're storing these qubits at the repeater, you're only limited by the length of sort of the longest link. And so instead of the decay rate being alpha L, it's now alpha L over 2, and so you get a much higher rate. And so you can just do this repeatedly. You could put lots of repeaters between Alice and Bob, and then you will increase the rate and it will depend only on the distance between the pair of repeaters. Okay, and so you can, for any distance between Alice and Bob, in principle, you can achieve a distance-independent rate by just spacing repeaters at, let's say, the same distance apart of L naught. Okay, I'll say that this distance independence is sensitive. It disappears if swaps are probabilistic, that they don't always succeed, and that happens with some technologies. If you don't have many memories, you will lose this distance independence, or if the memories are low quality. Okay, and I want to talk a little bit about the latter. Suppose that what you have is each repeater for each link has a single low quality memory. And let's say the qubit lifetime is just one slot, just enough time to attempt to generate a Bell state and then swap the Bell states if they're created. And suppose that the Bell state generation probability is P, and we have little n links. Then you succeed only if you're able to generate all of the Bell states across all of the links in the same time slot. And then you can swap everything and you're done. And as you can see, that's going to be p to the power little n. And so now that is decaying exponentially, essentially with distance. That's something we'll come back to distance independence. Okay, so we've talked about linear repeater networks, and there's been a lot of work on that, and a little of experimental work in the case where you have a single repeater. Challenges that arise are that swaps can be probabilistic, may not always succeed, and it makes for a fascinating analytics problem in the case where chains have sort of limited amounts of memory and maybe they're very noisy. I know there are a number of people trying to come up with reasonable ways of sort of evaluating their performance analytically. Now, this isn't what we think of as a network, but it turns out that it's important. It's something that I've only come to appreciate recently, because what we usually think of as a single network link, let's say between Chicago and Orlando, it's going to have to be implemented by putting lots and lots of repeaters on that link. And so the better that we can understand these linear repeater networks, the better that we'll be able to understand quantum networks. So let me talk about what I think of as a quantum entanglement network. We have quantum switches or repeaters. They have memories. They're connected via lossy links. The links generate entanglement, and then the noisy switches essentially swap a successfully generated link entanglement to propagate the entanglement to the end nodes. And I should say that there are two architectures that the community is looking at. I'm going to focus really on the first one, which is this architecture which is concerned with creating and distributing Bell states. But there's a second architecture that looks much more like a classical network, where what you do is you just use the network to transmit quantum information directly between Alice and Bob, okay? And what that does, in order to deal with loss and noise, it has to rely heavily on quantum error correction. And that field is really at its beginnings and nowhere close to being mature enough to really consider for deployment. The entanglement distribution network is sometimes referred to as a first generation network. It's often sometimes referred to as a two-way architecture because it turns out to require classical information to be sent back and forth. But it's considered to be the likely first generation network that gets deployed. Second architecture, is, you'll see it referred to as third generation. I won't talk about second generation. And it's considered to be much more far-term. So we're going to talk about the first. Okay, so here's a list of some of the challenges, at least, that we've been looking at with my colleagues. We're worrying about these memories that are noisy and that have finite lifetimes, worrying about gate and fiber noise. Once you start going up the stack, you start to worry about how should you allocate resources among different applications, which means how do you do path selection, how do you schedule resources or links between applications. There are interesting problems about how to sort of design the data and control planes. I'll say a little bit about that later. And I sort of come from the Sigmetrics community. A lot of what I'm interested in is really performance. What's the capacity of a network? How do you model it? How do you do measurements? And so on. And so I'm going to be touching on a number of these, but all in the context of this idea of worrying about loss or worrying about noise. And so I'd like to start by talking about some early work that we did on routing and path selection, because it's sort of nice in the way that it sort of deals with this rate independence that distance independence that I was mentioning before, okay? And the idea is we have a network, let's say it's a 2D grid, and we have, let's say, Alice and Bob located on the network. And what we want to do is, instead of having like a single path between Alice and Bob, to try to use the resource diversity to increase performance, increase the rate between Alice and Bob. And at the same time, we're sort of curious, what are reasonable rules that the switches should run for choosing or selecting the paths. And so we looked at a single flow, multipath. We were concerned about local versus globe link in state information, and I'll show you a result for that. We'll assume that P is the probability that a link succeeds in generating in a Bell state, and that it's independent for all of the links, and that we're running the same process as before. We generate link level Bell states, and then we decide which ones to swap. And so in the second diagram, I'm showing an instance where some of the link level Bell states are there. And then if you look at the switches, some of them are essentially doing swaps. And if you look at what's available between Alice and Bob, you see that there are two connected paths. And so in this instance, Alice and Bob are able to generate two Bell states between them. Swaps are probabilistic, and Q is the probability that a Bell swap succeeds, okay? And we looked at several policies. What I'm showing you in this 3D graph is essentially the logarithm of the rate, and on the X and Y axes is just the horizontal distance and the vertical distance between Alice and Bob. If you use global link state knowledge, then you get the surface that's sort of at the top. And one thing to notice is that it does exhibit a slow exponential decay, so that in the best of all worlds, as Alice and Bob get farther and farther apart, they will get lower and lower rates between them. The bottom surface corresponds to the case where you just pick the shortest of the paths that get created between Alice and Bob, and you just use that as if it were a linear repeater chain. And then in the middle is the performance when the switches use a very simple local rules to decide what to swap. And what you see is that this simple heuristic is able to get you, it's a rate that does not decay as fast as if you only use a single path, showing that there's a benefit in using this resource diversity that's available here. On the other hand, you still see this exponential decay. And so that sort of got us sort of thinking about if there was any way that we might be able to get around that. And it turns out that the answer is yes. And what you do is the following. I'm showing you a switch on the left with 3 link level Bell states that were successfully prepared. And in the schemes I was showing you before, the switch would have only picked 2 of them to do a swap on, and it would have just wasted the 3rd. It turns out that there are measurements, or if you want, sort of like generalized swaps that the switch could do that could be used to entangle all 3 of the qubits at the end of the links. And what that does is it generates what's referred to as a GHZ state, in this case, a 3 GHZ state. And you can think of it as just sort of a generalization of a Bell state, but when you have more than 2 qubits. And I'll just mention that this is useful for lots of applications, although I'm not going to go into them. I'm just going to talk about it in the context of routing. Okay, so when might that help? Suppose that we have the following configuration on the left. Okay, these were the successfully generated link Bell states, and the switches decided which pairs to swap or to measure, showing with the yellow lines linking them. And what we see is that there is no connected path between Alice and Bob, okay? And the problem is that that switch with the red X essentially swapped the wrong pair of Bell states. So if that switch had instead performed a 3 GHZ measurement, then you would have gotten a connected path between Alice and Bob. And so that sort of gives rise to protocols like what I'm labeling here as 3 GHZ and 4 GHZ. 4 GHZ is easy to describe. You measure up to 4 entangled links. But if only 2 of them come up, you measure them. With the 3 GHZ, you measure up to 3, and if there happen to be 4, then you just randomly pick the 3 to measure. And what I'm showing in the graph here is the areas where you get distance-independent rate as a function of, on the y-axis is the Bell state success probability for the link, and on the x-axis is the swap success probability Q. And if you look at the region, what will happen here is you can map this to a site bond percolation problem, a problem well studied in physics, and you find that there are regions in this sort of PQ space where you get percolation, and I'm showing one right at sort of the top right corner, and there, if the link level success probability P and the swap probability Q fall in that region, you get a rate that is independent of how far Alice is from Bob. And if you use the 4GHZ protocol, you get even a larger region. And so both of these achieve distance-independent rates. And this is whether, even in the face of loss, in the face of, let's say, very few memories, in the face of very short-lived qubits in the memories. Okay, I'd like to talk a little bit about performance and in terms of network capacity and resource allocation, and drawing on some work that I've done with collaborators here. We're going to look at a single quantum switch, and let's suppose that it's connecting a bunch of users. Okay, think of it, it's the simplest quantum network that you can think of. And what the user pairs do is they generate requests for bell states. Okay, and so this switch is going to operate just as I had described before. It's going to repeat a bunch of phases. The first phase, the links randomly generate bell states, let's say shown by the solid black lines. And then in the second phase, the switch has to decide which of the link level bell states to swap. Okay, and it turns out that this problem of choosing which ones to swap corresponds to selecting an eligible matching in a graph among memories. In the figure that you have below, think of it that the red circles correspond to successfully created bell pairs, and the dashed lines between them correspond to that there is a request to essentially swap those to generate an end-to-end bell pair. And what you would do is you would come up with a matching, and the outcome of that essentially determines the swaps that the switch performs and the set of end-to-end entanglements that get created. And so it turns out this is not too far from the problems that arise in classical networks having to do with scheduling switches. And so we've been able to adapt classical policies to this setting. And so you can characterize what the maximum capacity region is for a switch like this. And by the region, meaning that the set of rates that the users would like to have, if they fall within that region, they can be handled, and if not, they cannot. And we've been able to do it in sort of memory-limited switches or switches that have large numbers of memories. And one nice thing about that is in the sort of the graph that I'm showing below, suppose that you have two request streams. The one memory per link essentially gives you the lower bound, the worst that you would do, and infinite number of memories per link gives you an upper bound. And so you know that anything where you have some, let's say, finite number of memories will fall someplace in between. You can show that a max weight scheduling algorithm is optimal. And what max weight means is that you associate weights to the edges in the previous graph that are essentially, oops, going the wrong way, that are increasing functions of the request queue length. And one thing that's interesting is if the users have lots of memory, then when there are no requests to be served, the switch can generate bell states that can just be stored at the users. And in that case, then when a request comes along, it'll be able to get the bell state with zero latency. Okay, so challenges that come up here is, I talked about this in the context of a single switch, and of course what we would really like to do is to be able to say something about an arbitrary network. It turns out that we have partial results for that, but the story is really very incomplete. Max weight scheduling is not a very easy, max weight matching is not an easy task. I mean, it is polynomial in running time, but it takes a fair amount of time, and so there's a need for work on lightweight scheduling policies. And the other thing is that here the focus has really been on throughput or capacity, and of course we'd like to be able to say something about latencies, how long it takes to sort of serve requests. Okay, so that's what I have to say about loss. And let me turn to noise. And let me introduce one of the techniques, in fact, the technique that has been proposed for dealing with noise when you're generating and distributing entanglement. And it's referred to as entanglement purification. Suppose that you have 3 Bell states, and because of noise, they're not of the highest quality. Then entanglement purification would essentially create some kind of quantum circuit that you would pass the qubits belonging to these Bell states through. You would then measure off all but one of the entangled pairs, and at the end, you would know that what was left would be of higher quality than any of the ones that you used to do the purification. And here's just a very simple protocol that I'm not really going to go into that takes 2 Bell states, one called the source pair, the other called the target pair. A very simple circuit using C0 gates, and then the target pair is measured off, both by Bob and Alice. They have to exchange the measurement results, and then Alice and Bob can determine whether they should throw away their source pair or whether they now have a higher quality Bell pair. And so the metric that's used for this, usually it's not the only one that's been proposed, is what's called fidelity. And think of it, it's the measure of closeness of the entangled pair of qubits that you have to perfection. And fidelity is in the range 0 to 1. 1 is complete fidelity, and as it goes to 0, you get decreasing fidelity or decreasing quality. Okay. And one thing about the circuit I showed you in the last slide is it can fail. And so there's a probability of success associated with it. And here what I'm doing is I'm showing the results if you do one step of purification between 2 initial Bell states where they have initial fidelity that's shown on the x-axis, and the blue curve shows what the final fidelity is if the purification succeeds. The red curve shows the probability that it will succeed. Okay, and so you sort of, in some sense, have a trade-off there. You lose rate because some of them are failing, but at the same time, you're increasing quality. Okay, so here I'm just showing what you get if the initial fidelities are 0.7. You can raise the fidelity to about 0.85, but the probability of success is a little under 0.6. Okay, so back to a linear repeater network. One way that you might make use of this, you have these links. Typically, these links consist of modes where you can attempt to generate a Bell state on each mode at the same time. They could correspond to, let's say, different frequencies in the light spectrum. They could correspond to different polarizations. They could be temporal modes in the sense that you could divide time up into frames. Each frame, let's say, able to, let's say, during that frame, you could attempt, let's say, K Bell state creations, and then you would just store them until the end of the frame. Okay. Suppose that the probability of success is P naught, which is, as we know, sort of a function of the number of repeaters. Well, because we have, let's say, M modes, then if all we care about is that at least one succeeds, then we increase the probability of successfully generating a link level Bell state a lot. The other thing that this does is in the case where we generate several Bell states across a link, we could purify them to increase fidelity. And so we might have some initial fidelity F naught every time we generate a Bell state, but then we would just purify, and the result would be, let's say, Bell states that have final fidelities that are larger than F naught. And so this ends up posing very interesting challenges. You know, what's the right purification algorithm design? And should we do purification across a single link, or should we swap everything and then purify end to end? Or should we break the path up into subpaths and purify over subpaths? And it introduces sort of very nice multi-objective path selection optimization problem where we worry about rate and fidelity. So with that in mind, we have looked at the capacity of a quantum switch where you want some minimum fidelity at the end. And we've been able to characterize the capacity region for different policies where either we purify end to end or we purify at the link level before we swap. And again, max weight policies achieves the throughput. If you look at the switch there, we have two request streams, and the graph below shows the rates that each of them can obtain. We see a very, very large region if we don't worry about noise, and that shrinks quite a bit when you worry about noise. We find often that you do better by purifying at the link level rather than purifying at the end-to-end level. Okay, I'd like to talk about another thing that comes up when you worry about fidelity, and that is if you have different orders in which you can serve, let's say, requests or qubits, how will scheduling affect fidelity? And so the example that I'm going to use is teleportation between a pair of users. And so we have Alice and Bob. They have noisy memories. Alice has teleportation requests, and what you're seeing are qubits to be teleported going into memory. And then at some point, a Bell state is created between Alice and Bob. And then the question is, which of the qubits in the request queue should be teleported? And let's say we pick the one at the head, and then it gets transferred. And what we would like to do is to understand how the scheduling could affect the average fidelity or the fidelity of the teleported qubit. So how should you schedule the Bell states or the data qubits? Should you do what you saw in the previous slide was oldest qubit first, or how about youngest qubit first? And then if these memories are finite in size, how should you manage the buffers? Do you discard the arriving qubit, or do you push out the oldest qubit? And here we're looking at some results for, let's say, a data generation rate of lambda, Bell state generation rate of mu. The initial Bell state fidelity is 0.9. Assume that the data qubits to be teleported are perfect. We have some sort of decoherence going on in the memories. We can store 10 qubits, looking at oldest qubit first, youngest qubit first, and push out management. And what the graph shows is the average fidelity of the teleported qubit as a function of lambda over mu, or the load. And I'm just going to dwell, these are sort of very interesting in the way they behave. I'm just going to dwell on the system where we use youngest qubit first universally. And so that corresponds to the light blue line, but it's overlapped by the yellow line when lambda is small. When the request rate is small, then what happens is that every time a data qubit comes in to be teleported, there's almost always a Bell pair there to teleport it. And so there's very little chance for decoherence. When lambda is larger than mu, when you're generating qubits to be teleported faster, then what happens is when a Bell state is created and comes in, you almost always have a recently arrived data qubit to teleport. And so you can do it without suffering much in terms of decoherence. And then when things are sort of balanced, then it turns out that the qubits have to stay in memory longer before they get used, and so you get the dip. And one thing is one can show that this youngest qubit first policy is actually optimal. It maximizes average fidelity and under sort of very general assumptions. I'd like to say one last thing before I stop, say a little bit about control plane. It turns out that much of the work is focused on, we'll call it hybrid classical quantum networks, where you have a quantum data plane and classical control plane. And there's a lot of work on extending software-defined networks to this. I just want to mention, it's interesting to ask whether you could have a quantum control plane, and without really going into detail, it turns out that a student of mine has come up with a way of using what's called a quantum walk. You can think of it as a quantum version of a random walk, but much, much more general, to propagate controls through the network. And he's had sort of very, very good success with that. And much of what he's doing these days is trying to apply it to distributed quantum computing and entanglement distribution. So to summarize, quantum networking introduces, in my mind, new problems, old problems with sort of interesting wrinkles, and there's just work to be done in terms of performance modeling, resource allocation, generation, distribution, and management of entangled state in noisy environments, what the control architecture should look like, network management, and then, of course, application to these different applications, application to computing, sensing, and so on. And research in this area is really in its infancy with many exciting problems. And so just closing remarks then, entanglement distribution is very different from data transfer. One thing that's very interesting is entanglement. Bell states are fungible. It doesn't matter which one you use. And so it suggests that it might be interesting to think about introducing storage overlay networks where you store Bell states, and then it might start to look like the future electric grid. I didn't talk about multipartite entanglement, but there's some analogy to multicast in the classical world. And then I'll just say the challenges, a lot of them have to do with memory and gate noise and how to deal with that. And then I've sort of presented all of this at sort of a level of abstraction. And so there's really a need to sort of connect these kinds of abstractions, these models to specific quantum technologies. I'll stop here.
So if you have a question, you can follow, and we already have one here. So please go ahead in your right.
Yeah, Robert Basmajan from Germany, Claushall University of Technology. Thank you for this very interesting talk, inspiring talk. You talked about quantum switches and quantum routers. And from my basic information, quantum computers require dilution refrigerators. What do you think about the quantum switches and quantum routers required? And if so, what do you think about the energy consumption? Because I'm coming from the energy part. Will quantum internet break our energy system?
Right.
This is one question. And
okay.
Second question, if I may. You talk about memories. And in these switches, you need to store some quantum states. And we know that quantum RAMs are not storing that much of information. Can you say something about this technology as well?
Okay, so going to your first question, almost all the technologies that are being considered are going to need refrigeration for the repeaters and for the switches. There's no getting around that. There is exploration of an all-photonic technology, and one reason that it's really being investigated is that it promises to be pretty close to room temperature environment. To be honest, it strikes me once we start to have these systems in place, there are going to be interesting optimization problems regarding energy use. You know, do you turn some things off? You can decrease quality by allowing the temperature to be higher. And so there may be ways, strategies for mitigating against the lower quality results that somehow would lead to more energy efficient approaches to getting solutions. So I would certainly at some point, maybe not right now, encourage someone like you to jump in and look at that. The second problem is, you're right, the memories, the number of memories that are sort of available are small. And so I confess, when I first started, I thought lots of memories. And as we've been progressing, our research has really been trying to focus more and more on the case where you either have only one memory, or it's really a very, very small number of memories. But I think a lot of what I talked about certainly applies in that case.
Thank you.
You can go ahead now on your right, and then we'll go to the left. Okay.
Thank you. Thanks for a great talk. This is Mai Zheng from Iowa State University. My question is about the potential impact of quantum memory on the existing memory and storage hierarchy. As you know, like today, the system, we have a very deep memory hierarchy consisting of many different technologies, like the SRAM for cache memory, DRAM for main memory, flash memory for permanent storage, and we may have a magnetic hard drive or even tape at the bottom. And we have many software abstractions designed for those layers. So I'm curious, when we have quantum memory, we will later introduce one additional layer in the existing hierarchy, or do you think the impact could be more more fundamental, we may need to consider the entire hierarchy. Maybe we no longer need a hierarchy anymore. We can achieve like high performance and low latency and big capacity durability simultaneously within one single combined layer. Could you comment on that, the potential impact of quantum memory?
Sure. So maybe first, quantum networks or quantum computing is not going to replace classical networks and classical computing. They're going to really sort of live side by side. So nothing having to do with classical memory hierarchies is going to change that I know of. Having said that, maybe there is some way that quantum could be used in that regard. What I took away when I first started, as you first started speaking, is I think there will be interesting problems having to do with a quantum memory hierarchy. And because the technologies really give very, very sort of different characteristics. You have something like ion trap, qubit technology promises memory lifetimes that could be on the order of, let's say, tens of seconds, maybe even minutes, but they have sort of slow transfer rates. Then you have, in the experimentalists that I work with, they use vacancy center memories. They have much shorter lifetimes, but they're faster to access. And so here, when I was suggested storage overlay network, in some sense, that is a hierarchy in that I would expect the repeaters would have a very different memory technology than the storage servers. And you could imagine what you might be doing is moving Bell states in and out between the two layers.
Yeah, thank you.
Thank you.
My name is Keshav from the University of Cambridge. Don, thank you very much for this wonderful talk. I had a question having to do with the ability for other researchers to work in this space. So one reason why networking became quite popular, as you know, is because of the abstractions were stable. So if you had a link, it was a link, and if you could have the link layer and work with link layer problems without worrying about routing and so on. So the abstractions that you presented in terms of the entanglement and so on, how stable are these with respect to the technologies? So if more specifically, somebody comes with a beautiful algorithm based on these abstractions, maybe 5 years from now, would it be the case that these abstractions are invalid because there's new technology?
That's an interesting, excuse me, that's an interesting question, which I don't have an easy answer to. When I think of what I've been doing, my initial abstractions didn't really capture everything that was important. And as I've worked in this field, I appreciate more and more the importance of noise, worrying about, let's say, memories, whatnot. I think that it's possible to come up with abstractions for, let's say, memories in terms of lifetimes, in terms of there are metrics called efficiency, whether you can retrieve things or not, that should capture it well enough to be able to sort of develop protocols. And then the technologies would end up sort of feeding in the parameter values. Having said that, it's possible that it'll still take a few more years before we really appreciate what these abstractions have to capture. But I'm hopeful.
Thank you.
So, Only from PNL, thanks for the great talk. I have a question about, do you have any comments on the similarity and difference between the general quantum internet and the quantum sensor network?
Okay, that's a good question. When I think of, let's say, a quantum internet as one that is essentially generating and distributing entanglement, all of the work that I've seen so far on quantum sensing would, for at least in a distributed environment, would use that entanglement. So I see a quantum internet as really quite useful for feeding the entanglement that would be needed for the distributed sensing.
Thank you.
Many thanks for the talk. I'm Matthijs Wintrekker from
Can you
India.
hear it? Because I
Could
can't.
you speak a little?
Many thanks for the talk. I'm Matthijs Wintrekker from India. So the question is, would the entire framework change if you work with topological quantum states?
Okay, so I confess I'm not that familiar with topological quantum states. I'm going to say something that may or may not be related. What I am aware of is that you can have quantum systems that are based on sort of discrete variable, and then you can have on continuous variable. I don't know if topological state is an example of a continuous variable system. Everything that I've talked about has been for sort of discrete variable quantum networks. There is work going on with, let's say, sort of designing the protocols when you're doing sort of CV or continuous variable sort of quantum computing or quantum networking. Some of it is similar, looks similar to this, and some of it is different.
Many thanks.
So please join me in thanking Don for this wonderful talk. Thank you, Don.